Okay, so today we're going to continue with optimization. So last time the problems were a bit on the easier side. These ones are a little bit more difficult. Not in terms of the actual calculation, but in terms of the thinking that's involved. Okay, so we looked at the farmer problem with the rectangular area and that one on manufacturing the optimal can. So we've got another problem here. Now, this one is a bit more on the mathematical side, so it's not much of a word problem like maximize the area or optimize the cost or anything. It's a bit more abstract mathematical. Okay, so we've got the following setup. So we have a unit semicircle. So a circle with radius 1, and we just look at the top part. So this is going to be x squared plus y squared equals 1. Okay, and we're only looking at the top part, so positive y values. Next, we're going to draw in a rectangle. Okay, so we draw in a rectangle that is above the x-axis, but is still within the circle. Okay. So the goal is to find the dimensions of this rectangle that maximize the area. Okay, so again, we've got this rectangle, and it must fit within the circle, but have maximum area. Okay, and that's the whole word problem. We need to figure everything out from there. So the first thing is, let's put some coordinates down so we can do some calculations. That bottom right corner of the rectangle there, let's call this point x0. Okay, so it has some coordinate x, and since it's on the x-axis, the y values are going to be 0. Now, if we flip over to the other side, that bottom left corner, that will then be minus x0, because it's on the other side. Okay. Then let's look at the top right. We've got a point there. Let's call that xy. Right, because the bottom point there has x, so the top one will also be x, and it has some y parts that we're going to call y. Okay, so with this in mind, we can work out our function that we want to optimize. In this case, we want to optimize the area, so we need some sort of area function. So the area is going to be, what's that going to be? Base times height. So if we go from the origin to the right point, that distance is going to be x. Right? Because the coordinates is x, so that distance is x. So the whole base will then be 2x. Right? Because you got x on the left, x on the right, so the whole distance there is going to be 2x. What about the height of the rectangle? Well, it stops at that top right point, xy, so the height must be y. So we've got area is equal to 2xy. Okay, so we've got our function. Now, if we're following the steps, understand the problem, write down the formulas, and so on, we've got the equation that we need to optimize. However, there are two variables. We've got x and y. We don't want that. So we need to eliminate one of the variables. Okay, so this area function has two variables. There, we only want one. Okay, so we need to eliminate. Let's keep the x and get rid of the y. You could just as easily swap it around and get rid of x, keep the y. That's up to you. Okay, so with all this in mind from the picture, how can we eliminate y from this equation? Okay, so this is all the stuff we know. We've got the function, we've got the coordinates, we've got the constraints, right? Because it has to be within the circle. Yes? Sorry? No, we're not there yet. That's the next step. So we want to eliminate the y. We've got x, we've got y. We need to use the constraints, right? It has to be in the circle to eliminate y. How can we do it? No, deriving next step. We're not there yet. something else. Clever, almost there. Yeah.
I have to make one of the solutions such that
From where?
from using negative text.
Perfect. Yeah. So we're going to use this equation and we can solve for y, or you can solve for x, but depends on which one you're eliminating. So y squared is 1 minus x squared. So y is root 1 minus x squared. Okay. You could have done it the other way, but then you would be eliminating x. Okay. But that's up to you what you want to do. Okay. So we're going to take that from the constraint, substitute it into a, and that's going to give us a of x, a single variable, 2x root 1 minus x squared. So we've got ourselves a single variable function. We can then optimize this. In our case, we want to maximize. Okay, so out of all the possible solutions we get at the end, we want the solution that gives maximum a. Okay, now we can do what you want and derive. So next step, we need a prime of x. Okay, and once we got the a prime, we set it to 0, solve for x. Whatever solutions we get, we pick the one that gives maximum a. Okay, so we want to do d by dx of all of this on the right-hand side. Okay, now we've got a product of two functions. We've got 2x as our first function, root 1 minus x squared as the second function. So product rule. So this is going to be equal to, we derive the first one, the 2x, so that will just be a 2. Second part stays the same. Plus, then we leave the first part alone, so 2x stays there. Times, and then we derive the second one. We've done that quite a lot last semester. So that's going to be minus 2x over 2 root 1 minus x squared. Okay. We can do a bit of cleaning up there. We've got 2 times 2 at the top. So we've got 4 at the top, 2 at the bottom. So that's a 2 at the top. So this will be 2 root 1 minus x squared. And then we got the minus. Okay, x times x, that's going to be x squared. And then the 2, like we said earlier. Okay, so that gives us our derivative. Now, next step, we take the derivative, we set it equal to 0, and we solve for x. Okay, so we're going to have 2 root 1 minus x squared minus 2x squared over root 1 minus x squared is equal to 0. Okay, first thing, we've got 2 and 2. We can get rid of that. So we get root 1 minus x squared minus x squared over root 1 minus x squared is equal to 0. Okay, now we've got this root 1 minus x squared in the bottom there. We don't want to deal with fractions like that. So let's multiply through by the denominator to get rid of that. Okay, so we're going to take everything and multiply by root 1 minus x squared. Okay, so for the first term, we've got root 1 minus x squared times another root 1 minus x squared. So that's just 1 minus x squared minus. And then we've got the numerator clearing out the denominator. So that's just minus x squared. Okay, so we've got 1 minus 2x squared. Or we can write that as 2x squared equals 1. So x equals 1 over root 2. Right, now we would get a solution plus or minus. But if we go back to our setup here, we said x was on the right-hand side. So 1 over root 2, that takes care of the right-hand side. And then the minus 1 over root 2, that would be on the left-hand side. Okay, so we've got our x value. Now we need to check if this is a maximum or minimum. Okay, it is a maximum, but for homework, you're going to check that. So check that this is a maximum. Okay, how are we going to do that? We can use the second derivative. So here, find a double prime at this x value. And for it to be a maximum, we know that that concavity should be down. So here, whatever shape we get, the second derivative must be negative, so it's going down. And then that means we are at a maximum. So homework, please check that. This is a maximum, but please check that. So we've got the value of x. Now the question was find the dimensions of this rectangle. So here, this x is just half the width here, right? X was just from the origin to here. The actual width of this rectangle will be 2x. So we can't leave our answer just as x. We need to write it out properly. So the width, that was 2x, so that's going to be 2 over root 2. Okay. Again, please don't just leave your answer as x equals something. Read the question to actually see what you need to provide. In this case, it was the width and the height. So width is this. Height, how do we find that? Well, that's the y value. We just go back up a little bit. There, on the right side, y equals root 1 minus x squared. You can use that to find y. Yeah, that will be 1 over root 2. Yeah, so that is the shape of the rectangle that will give us maximum area. Okay. Any questions on this example? No questions. Okay. Let's have a look at the next problem. So the next one is going to be a homework exercise for you to try. So I'll set it up and then you can finish it for homework. Okay, so example 2, homework exercise. Okay, and very good test question. Okay, so what we're going to do is derive Snell's law. You would have seen that in high school, using Fermat's principle of least time. Okay, so Snell's law, you know, Fermat's principle of least time. I'll explain that to you. I'll set up the problem, and then you can do the rest as an exercise. Is there anyone that doesn't know Snell's law? You don't. Okay, there's a few. You don't know Snell's law? You didn't do it in matric? Okay. We'll do a quick physics lesson and then you can do that. Okay, so we are going to derive Snell's law using Fermat's principle of least action. Least time, sorry. I'm surprised you didn't do Snell's law. It's weird. Okay, so quick physics lesson. So what is Snell's law? Okay, so let's say we've got two mediums, right? So you need to imagine a situation where light is going from one medium to another medium. So the light can be going from air to water, from air to glass, glass to water, something like that. So from one transparent medium to another. So we got some medium here. Let's say this is air. And we've got some other medium here. Let's say this is water. Right, something transparent for the light to go through. Okay, so in air, let's say the light goes along this path here. Okay, at some angle. And the way we measure this angle is with respect to the normal. So we've got that horizontal line there, the normal, that will then be the vertical line. So we draw a vertical line, that will be the normal, and we have some angle here, theta 1. Okay, so the light comes in at an angle theta 1, and because of some physics stuff we won't get into, the light will then enter the water at a new angle theta 2. Okay, so it goes off like that at some theta 2. Okay. Now, depending on what is called the refractive index of these two mediums, the light will go at a certain speed. So in air, light goes at the speed of light. However, in water and glass and so on, the light is actually slower by some amount. The amount by which it is slower is given by the refractive index. So we have the refractive index. This is given by n, okay, some number, and it is the ratio of the speed of light, c. So that is just the speed of light as is, not traveling through something, divided by the speed of the light inside whatever the medium is. So inside air, there's going to be some refractive index because the light will have some certain speed. And then inside water, it will have a slower speed. Okay. So that is the refractive index, and it depends on the material that the light's going through. Now, what Snell's law says is that this top part, that air part, that angle there, is related to the bottom part with that angle theta 2 by this equation. So n1 sine theta 1 is equal to n2 sine theta 2. Okay. N1, again, that's the refractive index for this top part. Speed of light c divided by the speed in that medium. So that's on the left-hand side. And then the right-hand side, when it's going through this new medium, it's going to have some refractive index n2 and some angle theta 2. Okay, and those are related by this equation. Okay, so that's Snell's law. Now, what is Fermat's principle? Fermat's principle of least time. Okay, so I'm going to redraw that picture. So it will be something like this. Okay, we've got that interface between the two mediums. So the top is air, bottom is water, or something like that. We have the light coming in at some angle theta 1, and it's leaving at some angle theta 2. So what Fermat's principle of least time says is that if the light starts out at this point at A and ends at this point at B, the path taken from A to the origin to B is the minimum amount of time. So the path taken by the light from A to the origin, so that line at the top there, then O to B takes the least amount of time. Okay, and you can see where the optimization comes in. So we want to find the path that gives the least amount of time. Okay, so it's going from A to the origin and then to B. Now, whatever path it takes, so, whatever angles are involved there, that path has the least amount of time. So if this light takes a different path, that will always be greater than this path over here, given by Snell's law. So any other path will take longer take longer than the path given by Snell's law. Okay, and we want to prove this. Okay, so I'll do the full setup of everything, and then you can just follow the steps. So you've got your time function that we want to optimize. You do the derivative, set it to 0, and then at the end you'll get out Snell's law. Okay, so let's redraw that picture and then put in some labels. So we're going from A to O, and then from O, let's do it like that, to B. Okay, so what we want to do is work out the time taken to go from A to O and then O to B. Now we know the speed in both cases. In the top case, the light is taking the speed v1, right? Because it has refractive index n1. And then at the bottom, it's going to take speed v2. So in the top, it has speed v1. And then in the bottom, it has speed v2. So we know the speed. We want to work out the time taken. So if we know the speed and we want to work out the time, what's missing? Someone said? Distance. Yeah. So we want to work out the distance. So the distance will be that length AO. That will be the distance there. If we can work out AO, we got the distance, we got the speed, we can work out the time. Same thing for that bottom part. Okay, so let's set up a right angle triangle so that this AO becomes the hypotenuse, and we know how to work that out. Okay, so we got the following picture here. Let's say that base of the triangle there is X. Okay, because we need something to label it. We're going to say the full horizontal distance from A to B is L, that whole distance. So if that first part is X, then the second part will be L minus X. Right, this full distance, let's call that L. Okay, is everyone okay so far? Okay, so the full distance is L, that first part is X, so the second part is L minus X. So it adds up to L. Okay, then we can put in our angles. This is theta 1, and this was theta 2. Okay, and these are right-angled triangles. Okay, so the distance OA, that distance there, we can work out. Let's call this distance A, just so we have everything there, and this one B. Okay, you can call it anything, it doesn't really matter. So we want to find that OA distance there. Or AO. So that's going to be the roots of what? Right angle triangle will be A squared plus X squared. Right, that's going to be that distance. Okay, what about the other side, OB? Well, that vertical distance is B, the horizontal distance is L minus X. So OB, that will be the roots of B squared plus L minus X squared. Okay, everyone okay with that? Okay. So we've got the two distances. We want the time taken. So let's say TAO. That's the time taken to go from A to O. So we know the distance. We know the distance now. And we know the speed. How do we get the time? We've got speed. We've got distance. We want the time. Well, how can we do that? You seem a bit iffy with that. You sure? I'm going to tell Mr. Evans to deduct marks. Okay. Do your little triangle, see what it has to be. Distance over speed. Okay. So we got the distance AO, and we're dividing by the speed, V1. It's your wake-up alarm. Okay. Then we're going to do the same thing for the other one, TOB. Again, distance over speed, so OB that we found over there. But now the speed is V2. So we got V2. Okay, so that's the time taken for the first segment, time taken for the second segment. So the total time T, which is going to depend on X, right? We've got the X there. This is going to be time taken to go from A to O, plus the time taken to go from O to B. Okay, is everyone okay with that? So that is the time function. So what you're going to do for homework is minimize that, right? Because we want minimum time. So homework starts from here. So number 1, minimize the time function. Oh, there's a pen. So you're going to minimize the time function, and then from that, you're going to get Snell's law. And I'll give you a little hint for that as well. So the minimizing is quite straightforward. Just do the derivative. You'll get some equation. So we minimize tx. Okay, set it equal to 0. That's going to give you some equation. And then number 2, you'll get Snell's law. Okay, and then a little hint for that. Okay, so if we go back to here, we're going to look at this triangle inside here. Remember what Snell's law was saying? We have the sine theta 1 and sine theta 2. Okay, so how do we get those? So here, sine theta 1, what is that going to be in terms of this triangle? Okay, we've got a triangle. We want sine of theta 1. What's that going to be? And that's circuit, TOA, all of that. Yeah, sorry, what's that? Arc sine. Oh, no, you're thinking too much. Circuit, TOA, just your normal ratios. It's the SO mean in circuit, TOA. Sine is what over what? Opposite. What's the opposite length going to be? X, good. And was the H mean? Hypotenuse. What's that going to be? AO. Yeah. Okay, so first hint, sine theta 1 is X over AO. Okay, so once you do your derivative and all of that, you look for X over AO and you replace that with sine theta 1. That's the first part of your Snell's law. Then the second part is we need sine theta 2. So we look at this triangle over here, this bottom one. Okay, so again, this bottom triangle here, sine theta 2, what is that going to be? Not X, L minus X, yeah? Over OB, good. So you just do that replacement once you do the derivative, and you'll see you get your Snell's law. Okay, any questions on this? No questions. Okay, looks like a very nice class test 3 problem. Okay, maybe you'll take the hint. Yeah. So you do your minimizing of t, that gives you an equation. You take your equation and you do that replacement. So when you see x over AO, you put the sine theta 1. When you see the L minus x over OB, you put your sine theta 2, and you should get Snell's law. If you don't, you've done something wrong. Yeah. So you just do the replacement. So x over AO, you replace with that. L minus x over OB, you replace with that, and you'll see Snell's law there. All right. Any other questions before we move on? All good. Okay. Let's have a look at some more problems. Okay. So number 2. Find the points on the parabola. Okay, y equals x squared. That is closest to the point 1, 4. Okay, again, it's not like a word problem that we saw last time. So we're not trying to maximize some farmer's land or anything. It's more mathematical. Okay, but the idea is the same. So you look at the problem, you understand what needs to be maximized or minimized, set up the function that needs to be maximized or minimized, do the derivative, and pick your solution. So in this case, we want to find the points, whatever xy point that is closest, xy on that parabola, whatever that might be, that is closest to the point 1, 4. So what does closest mean? Closest means the distance is a minimum. Okay, So that's the function that we need to minimize. We need to come up with some function that gives us the distance between the 2 points. We minimize the distance to get the closest point, and then solve. Okay, so I've done our step 1 and step 2. Okay, so step 3 from that list of steps, set up the function. So what do we have? We've got some parabola, y equals x squared. We've got some points over here, 1, 4. We've got another point, xy. Sorry, that's a y. And there's some distance between them. We want to minimize that. Okay, so the distance of that dotted line, we want to find a function for that and minimize. Okay, well, that's just the distance formula, right? So the distance, d, is going to be the root of 1 minus x squared plus 4 minus y squared. Right, that's just your normal distance formula. Okay, if you didn't know that, you're in trouble. Okay, now this is a function of 2 variables. We've got an x, we've got a y. That is not going to work out. We need a single variable. So either we eliminate x or we eliminate y. Which one's easier to eliminate? Y. Why do we eliminate y? Because it's the function, yeah. So y equals x squared. We can put that in. So here d is equal to the root of 1 minus x squared plus 4 minus x squared squared. Now, since we've got this root here, it's going to make taking the derivative a little bit more confusing than needed. So instead of having this function d as our optimizing function, I'm going to define a new function f, which is going to be d squared. So this is going to be 1 minus x squared plus 4 minus x squared squared. Okay, so why can I do this? Okay, and the reason so minimizing the distance is equivalent to minimizing the distance squared. Yeah, those are equivalent, and I'll let you think about that. Okay, so instead of minimizing d and getting some answer, that's going to give us a lot more work because of this root. Instead, we're going to minimize d squared, and we're going to get the same answer. Okay, if you don't believe me, try minimize d and see what you get. Then we're going to minimize f, which is d squared, and you can compare your answers. Okay, so we've got f. That's going to be d squared, so all of that there. Yeah? Oh, sure. Okay, plus 4 minus x squared squared. Okay, so we've got our f function. We want to take the derivative, set to 0, solve for x. So f prime, what's that going to be? Okay, we've got a bit of a chain rule situation here. So 1 minus x squared, the 2 is going to come down. So it will be 2, 1 minus x. And then on the inside, we've got the derivative of minus x. That will be minus 1. Plus. Then again, the 2 is going to come down. So we've got 2, 4 minus x squared to the 1 now. And then derivative of the inside, that will be minus 2x. Okay, and all of that's going to be 0. Okay, now we need to solve for x. Okay, and whatever x solutions we get, we choose the one that gives us the minimum. Right, if we get 2 solutions, we need to check. One of them will be the minimum, the other one, might be the maximum. We need to be careful which one we pick. Okay, so let's simplify the brackets a bit there. So in the first case, we've got minus 2, 1 minus x, And then we've got a minus 4x from the other term there. 4 minus x squared. Okay, we can divide both terms by minus 2. That'll simplify this a bit. So we're going to have 1 minus x plus 2x 4 minus x squared. Okay, there we got something like that. Okay, now we can distribute the 2x inside there. So we're going to have 1 minus x plus 8x minus 2x cubed. Okay, so we got something like that. Minus x plus 8x, that will be a plus 7x. Okay, we got something like that. We need to factor this to get our x solutions, or you can do a guess and check or something like that. So what do we get for x when we factor this? You know how to factor these? Okay, try it out, see what you get. So it's x cubed, so we're going to get something from this. You got something?
X1 is 1,9.
Let's write it out here. It's pen again. 1.94.
So it's negative 0.94.
Okay, so let's write these out here. So x1, 1.94, x2.
Negative 1, negative 4.
Yeah,
Negative 3 is negative 1.7.
negative 1.79. Okay, so we've got three answers. Now we need to pick. One of them will be the minimum. The others, there'll be something else. Okay, so given x1, x2, x3, what we want is these f values. And then we choose the smallest one. So f of x1, what's that going to be? So that's this f that we got there. $5.13. Okay, then x2, what do we get for that? $18.44. Right, that's already bigger, so we're not interested in that one. The last one, let's see if it's the smallest.
Zero.
41. Okay, well, it's definitely not that one. 41 points?
That's 1.
31. Yeah, point.
31. 41.31.
Oh, 41.31. Okay. 41.3. Okay, well, it's definitely not that one. We want the smallest. So that will be the first one there. Okay, so that's going to be the minimum there. Right. Any questions on this one? Okay. Again, remember, don't just leave your answers in terms of those X's. We want the minimum one. So please, circle the minimum one or something like that. Cross out the other two. But I need to see, which one have you picked? Okay. Again, any questions before we move on? All good. Okay. Let's have a look at the next one. Number 3. This one's similar to the previous one. So we've got the following setup. So we've got the line y equals 2x plus 1. Right, just a straight line there. Then we're going to have some point q. We don't know what that is. Okay, and we've got another point p, which we do know is 2, 2. Okay. Now, the question is, find the minimum distance between P and Q, okay, like we had before. So we're going to have some minimum distance line between them. Okay, so that's part 1. And then part 2, show that this line PQ is perpendicular to the straight line. Okay, so again, we've got this minimum distance here, PQ. That's part 1, find that line. And then part 2, show that the PQ line is perpendicular to our straight line. So we need to show this is at right angles. Okay, so everyone clear on what we need to do? Okay, so let's have a look at part 1, finding Q. Once we have Q, then we can find that line and then show that it's perpendicular. So part 1, find the point Q. Okay, we're going to do it exactly the same as we did last time. So we got this point, we got Q, we don't know what Q is, it's some XY. We want the distance between them. So D for distance, that is the roots of, let's say, Q will be some XY, so X minus 2 squared, and then the Y value minus 2 squared. Okay, and again, same reason as before. We're not going to work with D, we're going to work with some function f, which is D squared. Okay, and again, we've got this issue of f having 2 variables. We want a single variable, so that y over there, we need to replace it with this 2x plus 1. Okay, so that's going to be x minus 2 squared, and then the y, that will be 2x plus 1 from the line. Okay, so that will be x minus 2 squared plus 2x, and then we've got a plus 1 minus 2, so minus 1 squared. Okay, so we got something like that. Now, we could do the whole chain rule, all of that, or you could multiply it out. So we've got x minus 2 squared. You could expand that out. Then you just get a quadratic that you want to take the derivative of, or you can do the chain rule. That works as well. Okay, so we want f prime. Let's go with the chain rule method. So we're going to take the 2 down. So that will be 2 x minus 2, and then to the power 1. The derivative of the inside, that's not going to do anything. Plus, then we've got another 2x minus 1. Now the derivative of the inside is 2. And we want that to be 0. Okay, let's simplify. So firstly, these 2's can go. So we're going to have x minus 2 plus 4x minus 2 is equal to 0. Okay, 4x plus x, so that will be 5x. And then minus 2, so minus 4 is 0. So x will be 4 over 5. Okay, so that is the point on the line that gives us the minimum distance. Okay, so if that's x, then y, that's going to be just the equation we had there. And then we're substituting x, so that will give us the x and the y that we need. Okay, so that's going to be 2 times 4, 8 over 5 plus 1. Okay, what's that going to be? 14 over 5. 13. Good. Okay, so we've got the x and the y pair for this point, Q. Okay, so that's part 1 done. We've got Q. Part 2, we need to show that this PQ line is perpendicular to the straight line. So part 2. Show that the PQ line is perpendicular to the straight line. Okay, so we need to find the equation of the line. So let's start by finding the gradients. So m, that will be y2 minus y1, x2 minus x1. Okay, and we've got the 2 points, so we can find the gradients. Okay, so let's say PQ, so y2, that will be the for Q, and y1, that will be from the P. Or you can do it the other way around, doesn't matter. So 2 minus 13 over 5 over x2 minus x1, so 2 minus, and we had x over here, which was the 4 over 5. Okay, what do we get for that? Negative a half. And we can stop there. You can find the full equation for the line if you want, but that's not needed. To show that they are perpendicular, the product of the gradients must be minus 1. Okay, so there's no need to carry on. So m1 times m2, that's 2 times minus a half, which is minus 1, which is what we needed to show. All right. Any questions on this one? No questions. Okay. Now, in fact, this works for a general curve here. So if I have some other function and I want to find the shortest distance, it will always be perpendicular to that curve. So in general, we have the following. So let's say, we got like a parabola from that first example. We've got some points over here, some points over here. There's going to be some minimum distance line like that. Okay. So that line, like our PQ line, will always be perpendicular to the curve. And by perpendicular to the curve, I mean perpendicular to the tangents. Yeah. But in the case of a straight line, well, the line's already straight, so there's no need to find the tangent. But if it is not a straight line, you can find the tangent, and that will always be perpendicular to that minimum distance line. So, fun fact, the minimum distance line is perpendicular to the tangent line of the curve. Okay, another homework exercise for this. Prove this for some function g. Okay, so now I don't even say what the function is, I just call it g. So what you're going to do is pick this point, whatever that point might be, find this line. Okay, so the minimum distance between some point and the curve g. Then find the tangent to G, G prime, all of that, and then show that they are perpendicular. Okay, so you can try that out for homework. Any questions for the homework problem? You're all good. Okay. Last problem for today. Number 4. Okay, so we've got the following setup. So we're going to have a sad face parabola like this. Okay, 1 minus x squared. So a sad face parabola shifted up. And what we're going to do is below the parabola, but above the straight line, we're going to draw ourselves a circle. Yeah. Okay, something like that. We've got the circle below the parabola, above the x-axis. What we want to do is find the radius of the circle that gives maximum area. Okay. Find the radius of the circle that gives maximum area. Okay, so this one's on the more difficult side of things. Okay, so we've got the picture. Okay, so we've got the function that we want to optimize, right? The area, pi r squared. We want to maximize that. And we've got the constraint, because whatever the circle looks like, it still has to be below the parabola. Okay, so it's going to start at the bottom there, but it can't go beyond the parabola at the top. Okay, so that's our function. That's our constraints. What can we do from here? So we've done that part 1, right? Understand the problem. We've done that. Well, what's the next step? Yeah. Hmm? It has something to do with it. Not quite. You're on track, but not quite. Yeah. Yes. 4? Yes, for the area of the circle, which needs. Yeah. But what do we need for the area of the circle? There's one thing we need. The radius. Yeah. So we need to find what the radius is going to be. So we need some equation for the radius, and then pi r squared. That will be the thing to maximize. Okay. Good. Okay. So we want to find the radius. What can we do? So, very close, not quite. It doesn't touch the turning point. It's a little bit below the turning point. Yeah. Perfect. Okay. What's that going to give us? Yeah, the circle's 1, but more importantly, what points is that going to give us? So when we substitute it in, we're going to get some intersection points, right? Well, where's that going to be? Very close. Sorry? Okay, sure. Right, so we sub that into the equation of the circle. So that means the parabola equals the circle, right? We substitute it in. What points is that going to give? No. Very close. Good idea, but not quite. Yeah, so we're on the right track. We're going to make the parabola equation equal to the circle. That's going to give us some points. It'll give us 2 of them, actually. What are these points after substituting? Sorry? Yeah, where are the points? In terms of the picture, where do I put the dots so I can show the points?
From the origin, because I think the negative goes to one other radius.
No, negative positive 1. That's the parabola roots. I mean, on the circle with the parabola, where are the points going to be? Yeah, you got the equation, but just for me to draw the points, where would it be? Right, you got the one equation equal to the other. That's going to give you the intercepts. You know where they cross. Where will that be? So I can draw them in. Yes. Yeah. Where they touch. That's going to be. There's going to be like one over there, one over there. They're going to touch on the 2 points there. Okay. Good. So we've got these 2 points. Technically, we only need 1 to find the radius, but that's fine. Okay. So we've got the 2 intersection points. Where would the center of the circle be? It's not halfway. It's a little bit down. Okay, think about the circle. What's the radius of the circle? So it's not from the turning point to the bottom, right? Where's it? Okay, the circle has radius 1, right? So ignore the parabola. We're not interested in that. Just the circle. Where's the center? So it's not halfway from the turning point to the origin. It's halfway from what? It's very obvious. Very obvious. Okay, think about the circle. The top of the circle to the bottom of the circle is diameter. The diameter of the circle is, someone said 2. So where's the middle? Y is 1, yeah. Okay, so we don't measure from the parabola down. We're just interested in the circle. Okay. So that's going to be somewhere here. Okay, maybe the picture's not too clear here with this drawing. It should be more like something like that. Okay, but the distance there is very small. Okay, so it's a bit hard to draw. Anyway, we've got something like that. Okay, so we've got the 2 intercept points. Let's redraw that here. So one over there, and we've got the center of the circle there. Okay, right? All good so far? Okay, and we know that middle point is at 0, 1. 0, 1. Okay. So what can we do from now, from this? Yeah, find the points. What's that going to be? Yeah, he was busy with it. So what's he doing? Not yet. Okay. Okay. So what do we do with the points once he found them? Distance formula. Yes. Good. Okay. So once we've got those points there, we can use the distance formula. Okay. Is everyone clear on that? Okay. So everyone knows what those 2 points at the top are from what he said earlier. Is everyone clear with that? Okay. And you know from the center to that outside point, that's going to be the radius. Okay. So once we have the radius, what do we need to find then? way back at the beginning. We needed the radius to find the, not the minimum, maximum area. Yeah, pi r squared. Once we got the radius, pi r squared, that gives you the area. Okay, so homework, find those intercept points. So you set the two things equal, find the intercept points, and then find the area. So we've got y equals 1 minus x squared. We're going to substitute that into x squared plus y squared equals 1. We're going to get the two intercept points. Once we have the two intercept points, find the radius and then the area. Solve for x. In 3, find the radius. And then once you have the radius, you get the area. Okay, and that will be the largest area because the circle is going to be touching the sides of the parabola. If the circle was any larger, it would go through the parabola. If it was any smaller, well, we don't want that. We want the maximum circle. Okay, good. So we've got this first part. Like you said, you got the points? Not yet. Okay, that's fine. We'll leave that for homework. So you've got the equation here. Solve for x, find the radius, and then find the area. Right. Any questions on this? You're good. Okay, and then something else to try that's very similar. Instead of a parabola, maybe we've got something like this. So upside down absolute value function. Okay, 1 minus the absolute value of x. You remember that guy from last semester. So we've got two straight lines, one with the positive gradient, one with the negative gradient. Same idea, we've got some circle inside there. Find the maximum area. So same idea as before, but now these two lines are going to be tangents, right? They're just going to touch the circle. So this positive gradient line, that's going to be tangent on the left. Then you can find that point. Then the one with the negative gradient, that will be the tangent on the right. Then we can find these points. Okay, we've got some center over there. We can find the radius and then the area. Okay, same idea. Okay, so that will be extra homework. Okay, so figure this one out over here, and then the same idea applies to this one here. Okay, any questions? No questions. Okay, we'll leave it at that for today. Next time we'll go through a few more problems like this, and then we'll start on the integral calculus section for antiderivatives. Okay, so if you look in the Stewart textbook, right after this section, the very last thing for differential calculus, you'll see there antiderivatives. Okay, please read through that first bit for Thursday.